Hello viewers, today we are going to discuss the topic on linear algebra, that is linear transformation. In this lecture we are going to discuss about definition of linear transformation, linear operator, linear functional, and then theorems based on linear transformation. And at the end of lecture we will discuss some examples related to linear transformation. So let us start our discussion with definition, how we can define linear transformation. So let V and W be two vector spaces over a field F, then a mapping P from V to W is said to be linear transformation if and only if for every x, y in V such that T of x plus y is equal to Tx plus Ty. You can take any x and y in vector space V in domain V, then T of x plus y that is equal to Tx plus Ty. Second, for any scalar alpha in field and for any x in V such that T of alpha x is equal to alpha time T of x. So if any transformation T from V to W satisfy these two conditions, then then it become a linear transformation. So we can also think about this. If V and W be two vector space over the field F, E is a transformation from V to W. If we take any x and y in V, the transformation of x, mapping of x is, that is T of x, output of x is T of x, and for y we get T of y in W. If we add these two, then x plus y belongs to W, x plus y belongs to V. So the output of this x plus y is T of x plus y, and it is nothing but it is the output of, it is the sum of Tx and Ty, that is T of x plus Ty. So if we add the elements of domain, then the output of that element is same as the output of their individual images, that is T of x plus y equal to Tx plus Ty. Similarly, if we take any alpha, any scalar alpha, if we multiply this alpha, this x with alpha, this alpha into x, then the output become T of alpha x, and it is nothing but it is same as alpha time T of x. That is, if we multiply any scalar with any element of V, then the output become of output of that element alpha of t of alpha x, that become alpha time t of x. If we multiply this beta by with y, then t of beta y is beta time t of y. So if t satisfy these two conditions from v to w, then t become a linear transformation. Second definition, that is linear operator. So let V be a vector space over the field F. Over field F. Then the mapping. Then a mapping T from V to V is said to be linear operator if and only if again it satisfies the same condition, that is for any x y in V such that t of x plus y is equal to t of x plus t of y. And second, for any alpha in F and for any x in V such that t of alpha x, that is equal to alpha time t of x. If t satisfies these two conditions from V to V, then t become a linear operator. Now definition number 3 is linear functional. The only difference in linear functional is that a mapping transformation T is defined from vector space to field, and all other properties remain same. Again, T is a mapping from vector space V to field, and T satisfies both the condition for any x, y in V such that T of x plus y, that is equal to Tx plus T of y. And second, for any alpha in field and x in, for any, you can take any x in V such that T of alpha x equal to alpha time T of x. Then T become a linear function. So in linear transformation, we define a transformation T from V to one vector space to another vector space. If we define from same vector space to same vector space, then it become a linear operator. If we define a mapping T from vector space to field, then it become linear functional. So this is the only difference, and all properties remain same. They satisfy all these two conditions, then it become a linear transformation, linear operator, or linear function according to their map. So now theorem. If V and W, V is a vector space over a field and W is a vector space over a field F, be two vector spaces over the field F. Prove that a function a function t from v to w is a linear transformation if and only if t of alpha x plus beta y is equal to alpha time t of x plus beta time t of y. For any, even I can write if and only if for any x y in v and alpha beta in field f such that t of alpha x plus beta y is equal to alpha time tx plus beta time t. So how we can prove this? We have to show that if V and W are two vector spaces over a field F, we have to prove that T from V to W is a linear transformation if and only if T of alpha x plus beta y equal to alpha time T of x plus beta time T of y. We have to keep this definition in our mind. The transformation T from V to W is said to be linear if it satisfies these two conditions, right? That is, T of x plus y is equal to tx plus ty. This is the additive property, and second is t alpha time t of alpha x equal to alpha time tx. So we start with if t is a linear transformation, if t from v to w be a linear transformation. So if t from v to w is a linear transformation, so let alpha beta in field and xy in vector. So because V is a vector space, so by the property of scalar multiplication, alpha x comma beta y, this belongs to V because V is closed under scalar multiplication. V is closed under scalar multiplication. Because V is a vector space, right? So can someone tell me what is the next step? Yes, alpha x plus beta y also belongs to V because V is closed under vector addition, right? Now, if this element belongs to V, now we have to find the transformation of this P of alpha x plus beta y. Now we have to find that T of alpha x plus beta y. If we take this alpha x to be u and beta y to be v, then T of u plus v, that is equal to Tu plus Tv, because T is linear transformation. And if T is a linear transformation, we can use the first property. So we can write this as T of alpha x plus T of beta y. Is this point clear? We use the first property because T is a linear transformation. So we can write it satisfies these two conditions. So we use this one, first one. So now because T is a linear transformation, so we can write T of alpha x, that is alpha time tx. It satisfies the second condition. Similarly, T of beta y, beta is a scalar, so we can write beta of beta time T of y. So we get the result. This implies for any alpha beta in field and for any xy in w, xy in v, such that T of alpha x plus beta y is equal to alpha time tx plus beta time ty. So this is the direct proof. Now conversely, so this, now we assume this part, right? So if for any alpha beta in field and for any x y in V such that P of alpha x plus beta y equal to alpha time tx plus beta time ty. This is the given condition. Now what we have to prove? T is a linear transformation. And how we can say that T is a linear transformation if T satisfy these two conditions? What are those two conditions? T of x plus y is equal to tx plus ty. And what is the second condition? T of alpha x equal to alpha time tx. So can someone tell me what are the choices of alpha and beta so that we can use this condition, because this is a given condition. We use this condition and we prove that T of x plus y equal to tx plus ty. But what are the choices of alpha and beta? So now our goal is to prove that T is linear transformation. T is a linear transformation. Right? So let this be start. So we make a, so choose alpha is equal to 1 is equal to beta. If we put alpha equal to beta equal to 1 in star, then T of 1 into x plus 1 into y, that is equal to 1 into, so we can write T of x plus y, right? T of x plus y, that is equal to this, and this is 1 time tx plus 1 time ty by using star, and this is 1 into tx, it is tx plus ty. So it satisfies the first condition, that is for any x y in V, even we can take for any x y in V, and alpha beta equal to 1. So for any x y in V such that T of x plus y, that is equal to tx plus ty. So it satisfies the first condition. Now second, let me write this as 1. Now the second one. Now for second, we have to prove that T of alpha x equal to alpha time tx. So what is the choice for the element beta, right? So beta, we can choose beta to be 0. So choose beta equal to 0. If we choose beta equal to 0, then T of alpha x plus 0 into beta, 0 into y, that is equal to alpha time tx plus 0 time ty, and alpha time tx plus 0 time ty. Ty belongs to w and 0 is a scalar. So this belongs to 0 into vector. This belongs to 0 vector, and it belongs to 0 w, because we take y in V, T of y in w. And if we multiply this by any scalar, 0 into ty, and that is equal to 0. But this 0, what is this 0? This is nothing but 0 vector. This 0 w. Why we write 0 w? Because it belongs to w. It is the 0 vector of w. If this belongs to, if we multiply this 0 into y, we get this is equal to 0 v. This is the 0 vector of v. So this 0 w is the 0 vector of 0 w is the 0 vector of w, where w is a vector space, right? So when Now this is the identity element. So we get alpha tx plus 0w, that is alpha tx. So t time alpha x is equal to, so that is for any alpha in f, x in v, such that t of alpha x equal to alpha time tx. So this satisfy both the conditions. Hence t from v to w is a linear transformation. So here take a pause of 30 seconds, pause, revise it, and then proceed. PR. Pause, revise, and proceed. So now let us discuss one example. Show that transformation t from R2 to R3 defined by t of x comma y is equal to x plus y comma x minus y comma y. This is a linear transformation. Show that this is a linear transformation. Okay. So we have to keep those two things, two conditions. Even because we have proved that T is a transformation if and only if T of alpha x plus beta y, that is equal to alpha time tx plus beta time t. So we can use this property. Okay. So now the domain is R2 and codomain, that is R3. So we take element in R2 and the output lies in R3. So let u is equal to x1 y1, this belongs to R2, and v is equal to x2 y2, this belongs to R2. We take for any alpha beta in field, here the field is, let it be R, and uv in R2, we have to show that T of alpha u plus beta v, that is equal to alpha time T of u plus beta time T of u. So this is our goal. We have to, if it satisfies this condition, then T is a linear transformation. So we start with left hand side, T of alpha u plus beta v. So T of alpha u, we can put x1 y1 plus beta x2 y2, that is equal to T of alpha x1 plus beta x2 alpha y1 plus beta y2. This is the sum of two vectors. Now T of x plus y, this is one vector, first coordinate, this is second coordinate. Now how we can define T? T of xy, that is x plus y, sum of first and second coordinate, then difference x minus y, then the second coordinate. So what is the output of this? T of, we get alpha x1 plus beta x2 plus alpha y1 plus beta y2. This is the first coordinate. What is second coordinate? Alpha x1 plus beta x2 minus alpha y1 minus beta y2. This is the second coordinate. And what is the third coordinate? That is y. It means second one. Alpha y1 plus beta y2. So this we use the transformation, right? We can take this as a star. So we can write here by using star. By using star. So now what is the next step? We have to take common. So we can write this as alpha x1 plus beta x2. Even we can separate them. We can take alpha to be common. So alpha, we can write alpha x1 plus alpha y1, comma alpha x1 minus alpha y1, comma alpha y1, and then plus beta x2 plus beta y2, comma beta x2 minus beta y2, comma beta y2. So we can take alpha to be common from first. So it become x1 plus y1, comma x1 minus y1, comma y1. We can take beta to be common from second. It become x2 plus y2, x2 minus y2, y2. And this is nothing but it is t of x1, y1 by transformation star, by using star. And this is nothing but this is t of x2 comma y2. And we have taken x1 comma y1 as u, so we can write this as t of u plus beta t of v. So t of alpha u plus beta v equal to this. This implies for any alpha beta in R, we can take field R, and for any u v in V, V means we can take R2 such that T of alpha u plus beta V is equal to alpha time T of u plus beta time T of V. Hence, T is a linear transformation. So, in this way, we can prove that T is a linear transformation. Now, next example, show that T from R2 to R3 defined by T of x comma y that is equal to x plus 1 comma 2y comma x plus y. So this is the transformation. Right? Now you can take this as a star. We have to show that this whether this is a transformation, linear transformation or not. Okay. So again, what we have to prove? T of alpha x plus beta y equal to alpha time tx plus beta time by ty. So let u is equal to x1, y1, this belongs to R2, and v is equal to x2, y2, this belongs to R2. Now, for any alpha, beta in field R, we can take field to be set of real numbers, and u, v in R2, even we have to show that. We have to prove that, to show that for every alpha, beta in R and u, v in R2, T of alpha u plus beta v equal to alpha time T of u plus beta time T of v. So this is our goal. Right? This we have to prove. So we start with T of alpha u plus beta v. We have already write how we can add. So I directly write here alpha time x1 y1 plus beta time x2 y2. So t of this become alpha x1 plus beta x2 alpha y1 plus beta y2. Now you make the use of equation star. This is alpha x1 plus beta x2. This is the first coordinate, right? This is first coordinate and this is also first coordinate. So what is output? First coordinate x plus 1. So alpha x1 plus beta x2 plus 1 plus 1. So this is the first coordinate. What is the second? 2 times of second, and this is second. So we get 2 times of this. So 2 times of alpha y1 plus beta y2. And what is the third? Third is sum of first and second. So alpha x1 plus beta x2 plus alpha y1 plus beta y2. Now this is alpha x1 if we add 1 here, alpha x1 plus 1 comma 2 times alpha y1 alpha x1 plus alpha y1. This is our first. Second, beta x2 plus 2 times beta y2 plus beta x2. Even I write beta x2 comma 2 times beta y2 comma beta x2 plus beta y2. So in this way we can separate this, but what we get, we cannot take alpha to be common from this, right? If we take this one with alpha x1, then there is no one constant one is added with beta x2, right? So we cannot write this as even we can take beta to be common here, but x2, this is the first coordinate, we get only x2, but what is here? What is how we can define the transformation? This is x plus 1, right? First coordinate add with 1. It shifted to x plus 1, right? So it means we cannot write this as beta time x2 plus 1. It means this we cannot write this as t of 3. Even we can directly, this is not equal to alpha time t of u plus beta time t of u. So even we can directly prove this. Otherwise, from this step, if there is a confusion, then you can take this as equation 1, and after this, what we do, we can separately find out alpha time t of u plus beta time t of b, right hand side. We separately find the value of this. What is this? Alpha time t of u. T of u is x1 comma y1 plus beta time t of b. T of b is x2 comma y2. That is alpha. What is the value of t x1 comma y1? So it is already defined. X comma y, x plus 1, 2y, x plus y. So here what we get? X1 plus 1, 2 times y1, x1 plus y1. This is the output of tx1 y1. Now tx2 y2, the same way we get x2 plus 1, 2y2, x2 plus y2. So when we add, we get alpha x1 plus alpha 2 alpha y1 alpha x1 plus alpha y1. Similarly, we get beta x2 plus beta plus 2 beta y2. Sorry, not plus, but comma beta x2 plus beta y2, and this is equal to alpha x1 plus beta x2 plus alpha plus beta, right? And this is 2 alpha y1 plus 2 beta y2, and x is alpha x1 plus alpha y1 plus beta x2 plus beta y2. So if we compare these two with 1, what we get? Alpha x1 plus beta x2 plus 1. But here it is alpha x1 plus beta x2 plus alpha plus beta. Second, so first coordinate is not equal, right? So if it is not equal, so we can say from first and second, we get T of u alpha u plus beta v is not equal to alpha time tu plus beta time. So you can also do like this. Either you can go through by this part, again you get the same result. If you face some difficulty in this step, then you can separately find the left hand side and then find the right hand side, solution of right hand side, and compare them. If both are equal, then it is a linear transformation. If not equal, then it is not a linear. So what we observe, if there is a constant, if we get any constant in the output of a transformation, then it is not a linear transformation. For example, if we define T from R2 to R2, T is a mapping from R2 to R2 defined by T of x comma y, that is equal to x plus y comma, even I can take 3 here. So this is not a linear transformation, because when how we can say this is not a linear transformation, we take u and v. U is equal to x1 y1 and v is equal to x2 y2. So what is T of alpha u plus beta b? That is T of alpha x1 plus beta x2 alpha y1 plus beta y2. How we can add this? What is the output of this? The output is first plus second. So alpha x1 plus beta x2 plus alpha y1 plus beta y2. This is the first coordinate and second coordinate is 3. So let this be 1. Right. Now we separately find the alpha time T of u. What is the right hand side? Alpha time T of u plus beta time T of v. So we solve this. We find the value of this. Alpha time T of x1 y1 plus beta time T of x2 y2. So alpha time, what is the value of this? This is x1 plus y1 comma 3 plus beta time x2 plus y2 comma 3. Right? So we get alpha x1 plus alpha y1 comma 3 alpha beta x2 plus beta y2 comma 3 beta. So if we add the coordinates, add these two vectors, so we get alpha x1 plus alpha y1 plus beta x2 plus beta y2. So it is same as the first coordinate. First coordinate is equal, but second coordinate we get 3 alpha plus 3 beta. So here second is 3, but here second coordinate is 3 alpha plus 3 beta. So this implies that P of u plus b, P of alpha u plus beta b is not equal to alpha time P of u plus beta time P of u. For any alpha beta in field R and uv in R2, such that this, hence T is not a linear transmission. Even in the above case here also we can write hence T is not a linear transmission. So in this way we can prove that T is, in first example we prove that T is a linear transmission. In second and third, what we have to, that T is not a linear transmission. Now next example number 4. Let V is a vector space over the field R of VR of is a vector space of integrable functions on R, right? So this is a integrable function. Prove that T is a mapping from V2, vector space V2 R. So it is a linear functional, right? Because T is defined from vector space to field, defined by T of, we can take function, integrable function f, and we get integration c to d f of x d of x for any c d in R and f belongs to vector. Okay. So to prove that, we have to prove that T is a linear functional. So this is this we have to prove that, right? So how we can define the mapping? Define T of f is equal to c to d f of x d of x. So let f comma g be any integral function in V, and alpha beta be any scalar that belongs to R. So if fg belongs to V, and what is T of f? T of f is c to d fx dx. What is T of g? Integration c to d g of x dx. Because this belongs to vector space, right? Now what we have to prove? We have to prove that for any fg in V and for any alpha beta in R, T of alpha f plus beta g equal to alpha time T of f plus beta time T of g. So this is our goal. So we start with left hand side. So T of alpha f plus beta g. It is c to d alpha f plus beta g time x d of x. It is by definition, right? So we can write this as c to d, or we can add two functions f plus g at at point x is how addition is defined. This is f of x plus g of x. And how the scalar multiplication is defined? Alpha time f at x, that is alpha time f of x. So here we can write alpha time f at x plus beta time g at x dx. And this is c to d alpha time f of x plus beta time g of x d of x. And we can separate this alpha time f of x dx plus beta time c to d g of x dx. So this is and c to d f of x dx is nothing but it is t of f plus beta time t of g. So what we get? This implies for any f comma g in V and alpha beta in field R such that t of alpha f plus beta g is equal to alpha time t of f plus beta time t of g. Hence t is a linear transformation. So in this way we can prove that. So please go through this, how we can show that even this is not a linear transformation, this is a linear functional. So this is a linear functional because T is a mapping from vector space to scalar field that is set of real number. Okay. Now next example is example number 5. Now we have Mn. Mn is set of all n cross n matrices over real number. Real numbers. So we can define Mn over R. So instead of writing, I can write Mn over R. Set of all n cross n matrices over, and we can take any matrix A that is Aij of order n cross n. This belongs to Mn. Right? Now, how we can define trace of matrix? Trace of matrix A, that is equal to summation I is equal to 1 to n Aii. How we can define trace? If we have matrix A, that is A11, A12, A13, A1n, A21, A22, A23, A2n, A31, A32, A33, A3n, and similarly AN1, AN2, AN3, ANn. So if this is a matrix, then the trace is sum of all principal diagonal elements. So this is, that is, trace of A is equal to A11 plus A22 plus A33 plus A44 plus AN. So we can write this as summation I is equal to 1 to n aii. So in this way, we can define trace of matrix. So trace of matrix means sum of all the diagonal elements, principal diagonal elements, right? So show that, now show that E is a mapping from Mn over R to real number R, defined by T of A. If we take any matrix A, what is A? A means any matrix that belongs to MNR. MNR means set of all n cross n matrix over the real number. And what is the output? We get trace of A. Trace of A, right? So we define by this. We have to show that T is a linear functional. Why we say it's a functional? Because mapping is defined from vector space to field set of real number. So now how we define given mapping is T of, we can take any element A from Mn R, that is equal to trace of A. Okay. So let A comma B be any matrix. This belongs to Mn R, set of all n cross n matrices over the real number. And alpha beta be any scalar from field set of real number R. Now here A is, because A belongs to MNR, so matrix A is like Aij. A is in the form of Aij of order n cross n, and B is equal to Bij of order n cross n. Now what is alpha A plus beta B? Alpha A plus beta B is nothing but alpha time Aij n cross n plus beta time Bij of order n cross n. And because it is a scalar, so we can add alpha Aij, we can multiply this by each element of the matrix, and similarly we can multiply beta with each element of matrix B. Now because the order of matrix, both matrices are same, so we can add, this become alpha Aij plus beta Bij of order n cross n. So this is our alpha A plus beta B. Now we find T of A, alpha A plus beta B. What is the output? How we can define? We have already defined this T of any matrix, that is trace of matrix. So T of alpha A plus beta B, what we get? We get trace of alpha A plus beta B. And what is trace of alpha A plus beta B? That is summation of I is equal to 1 to n. What is the trace of this matrix? Trace of this matrix is alpha aii, because sum of diagonal elements of matrix A, that is aii, and sum of diagonal element of bij, that is bii, even because we can take here I. So this is alpha aii plus beta. So we can write this as, this is nothing but this is alpha I equal to 1 to n. We can separate them plus summation I equal to 1 to n beta bii. We can take alpha to be common, I equal to 1 to n aii plus beta times summation I equal to 1 to n bii. So it is alpha time t of trace of a plus beta time trace of b, and trace of a means t of a, and beta time this is t of b. So this implies for any alpha beta in R and AB in Mn matrix of order n cross n over R, such that T of alpha A plus beta B is equal to alpha time T of A plus beta time T of B. Hence, T is a linear function because T is a mapping from vector space to field. Okay. So let us discuss one more example. V is a vector space. V is a vector space of polynomial. V is a vector space of polynomial functions from a field F into F, defined as h of x is equal to c0 plus c1x plus c2x square plus cnxn, where for all ci belongs to field F, for all I lies between 0 to n, and d of hx, that is equal to c1 plus 2 c2x plus 3c3 x square plus ncn x raised to power n minus 1. This is the operator d, defined as d of hx equal to this. Prove that d from v to v is a linear operator. So we have to prove this. So let fx comma gx, this be a polynomial, and this belongs to v, right? So if fx belongs to v, then fx is a polynomial like a0 plus a1x plus a2x square plus anxn, such that ai belongs to field F, I lies between 0 to n. So gx is also look like b0 plus b1x b2x square bnxn, such that all bi's belongs to field F and I lies between 0 to n. And we take alpha beta be any scalar from field F. Now What is alpha time f of x plus beta time g of x? This is alpha time a0 plus a1x plus a2x square plus anxn plus beta time b0 plus b1x plus b2x square plus bnxn. So that is alpha a0 plus alpha a1x plus alpha a2x square plus alpha anxn plus beta b0 plus beta b1x plus beta b2x square plus beta bn x raised to power n, and we get alpha a0 plus beta b0 comma, then we can add alpha a0 plus beta b0 plus alpha a1 plus beta b1. We can take x common, alpha a2 plus beta b2 x square plus alpha an plus beta bn x raised to power n. So we can take the terms of add constant term with constant term. We can combine the terms of x with terms of x. So first polynomial with second. So this become alpha a1 plus beta b1 time x, alpha a2 plus beta b2 time x square plus so on, right? So this is our alpha f of x plus beta g of x. If we apply the operator d on alpha f of x plus beta g of x, what is the output of this? We get first term to be, because d act as a differentiation derivative, right? The derivative of constant, this becomes 0. So what is the derivative? Second one, this x ka derivative 1 ho gaya, so it become alpha a1 plus beta b1. Similarly, 2 time alpha a2 plus beta b2 is x plus so on, plus n time alpha an plus beta bn x raised to power n minus 1. So this is the derivative of the above polynomial. So d act as a differential operator, right? So this is, let this be equation 1. Now what we have to prove, it is equal to alpha time d of fx plus beta time d of gx, right? So we can take terms of alpha to be common. Even without taking this as equation 1, we can take terms of alpha to be common. So alpha a1 plus 2 time alpha a2 plus n time alpha an x raised to power n minus 1 plus beta a2 beta b1 plus 2 time beta b2 plus n time beta bn x raised to power n minus 1. So we can take alpha in common in first term, and this become a1 plus 2a2, even we get 2a2x, b2 b2x, 2a2x plus n an x raised to power n minus 1 plus beta time b1 plus 2b2x plus n bn x raised to power n minus 1. So this is alpha time d of fx plus beta time t of x. So this implies d is a linear function. So in this way we have discussed examples so related to linear transformation, linear operator, and linear functional. So this is a linear operator, not linear functional. This is linear operator. So now assignment to all of you. V is a vector space of all n cross n matrices, order n cross n matrices, and P, we take P is a fixed matrix. P is a fixed n cross n matrix. This matrix P is fixed, right? We define a mapping P from set of all n cross n matrix to same V to B, right? So now how we can define this? P of A, that is AP minus P of A. And second, we define P of A is equal to AP plus P of A. Show that P is a linear transformation. P is a linear transformation. So this is an assignment question to you. Keep this thing in mind. Okay. That P is fixed, right? So if we multiply it with a fixed number, what happens, right? If we, in real number, if I take 2 into P into A, P into even I can say 2A. So here 2 is fixed. Only change in this. Okay. So similarly, P is a fixed matrix. This is given that P is a fixed matrix. Now, what is the output of any matrix A? A into P minus P into A. Now, what we have to prove that? What we have to show that? Is it a linear transformation? So, if we take any two matrices, A and B, then T of alpha A plus beta B, that is alpha time T of A plus beta time T of B, is it true? If it is true, then it is a linear transformation. But what is T of A? T of A is AP minus PA. So you can use this. Right? So this is all about linear transformation. Thank you. Revise this content, whatever we have discussed in today's lecture. Thank you. Have a nice day.